In this lecture, we are going to study about semiconductor lasers, its structure, material, and characteristics. This is lecture 5 of Unit 3 Optoelectronics. Now, semiconductor lasers are of two types, except the construction, principle, and working are same for both. Now, that is homojunction semiconductor laser and a heterojunction semiconductor laser. We shall see what is a homojunction and what is a heterojunction laser. A homojunction semiconductor laser uses the same semiconducting material with a different doping on both the sides of the junction, whereas a heterojunction uses two semiconductor materials having different band gap energies on both the sides of the junction. What is the basic principle on which it functions? Now, in conventional lasers like ruby, helium neon, laser light are generated due to transition of electrons from higher to lower energy levels. But in semiconductor lasers, the transition takes place from conduction band to the valence band. We know that free electrons are in the conduction band. Laser light is produced due to recombination of electrons and holes at the p-n junction when current is passed through the diode. Laser light is due to stimulated emissions. Now, when current is passed through a p-n junction under forward bias, the injected electrons and holes will increase the density of electrons in conduction band and holes in valence band. As the current is further increased at some threshold value of current, the amplification will take place and laser begins to emit coherent radiations. The properties of semiconductor laser depends upon the energy gap. This is the picture of a semiconductor laser. We have got the p-type material and the n-type material, and the junction lies over here in between. Okay. Then we have got metallic contacts at the top surface and at the bottom surface, and the p-n junction is forward biased. You would see the p-type material is connected to the positive terminal of the battery, and the n region is connected to the negative terminal of the battery, and this is a variable power supply. Also, the three surfaces of it are roughened, whereas only one surface is partially roughened or partially polished, so that laser light will escape only from this side and not from the other three sides. This is the energy diagram wherein there is no biasing and it is forward biased. We know that EV is the maximum energy of the valence band and EC is the minimum energy of the conduction band. P indicates P region and N indicates N region. When the p-n junction is forward biased, the electrons will move from the n region towards the depletion region, and holes also move from the p region towards the depletion region. How do you define what is the depletion region? It is a region which does not have free electrons and holes when there is no biasing. But when there is biasing, then what will happen? The electrons will come in from the n side and holes will come in from the p side. So in this region, the depletion region, there is a population inversion. That is, there is more number of electrons and then the holes. Now there's a recombination of electrons and holes in the depletion region. When they recombine, they give out light, that is laser light. What is the working of this? When the junction is forward biased, electrons from n region and holes from p region move to cross the junction in opposite directions. In the junction region, the electrons and holes recombine due to transition of electrons from conduction band to valence band. For low currents, population inversion does not take place. Hence, only spontaneous emission takes place and the photons released are not coherent. So, below a threshold current, it is all spontaneous emissions. When forward current is further increased beyond the certain threshold value, population inversion takes place and coherent photons are released. The energy gap of gallium arsenide is about 1.487 electron volt and corresponding wavelength of radiation is 6435 angstroms, which is responsible for laser emission. Then we can see What are the characteristics and applications of semiconductor lasers? The characteristic properties are directionality, negligible divergence, high intensity, high degree of coherence, and monochromatic. Applications, we've got various applications. Some of them are like in communication, in medical, in industry, chemical, and biological. So now shall see what is the difference between a LED and a laser. In terms of material, you can see both have got a PN junction. Biasing, both the LED and the laser are forward biased. Major differences: in the case of LED, light is given out by spontaneous emissions, whereas in the case of laser, light is given out by stimulated emissions. That is why this LED, it is incoherent, whereas laser, it is highly coherent. LED is non-directional, whereas laser is directional in nature. So in this lecture, we have studied what is a semiconductor laser.